For decades, relational databases have functioned as the default choice for enterprise data storage. This dominance is deeply embedded in the software profession. An architect starting a new project typically focuses on choosing a specific vendor, like Oracle or Microsoft, rather than evaluating different database paradigms. Various alternative technologies have attempted to capture a share of this enterprise market over the years. In the 1990s, object databases were positioned as a serious challenger, yet they failed to achieve widespread adoption. Today, NoSQL databases are experiencing a different outcome, capturing significant and sustained market share across the industry. This disruption is a genuine surprise to veteran software professionals who have worked within the relational consensus for their entire careers. Because NoSQL is maintaining its trajectory, we have to look back at the core computing problems relational databases originally solved. Only then can we see why a different architecture is now required. The first problem of computing is physical data storage. Computer architectures rely on main memory, or RAM, to handle immediate operations. It is fast, but strictly limited in physical capacity. Main memory is also volatile. If a server loses power or the operating system crashes, all data held in that memory is erased. To protect information, system architecture separates this fast, volatile memory from a much larger, slower, persistent backing store. In a critical system failure, everything in volatile memory is erased. The data in the backing store remains intact. Writing data to this slower, persistent layer is a requirement for keeping information alive long-term. Bridging the performance gap between fast main memory and the slow backing store is the primary function of any database system. Without a persistent backing store, an enterprise application is incapable of surviving basic hardware disruptions. Once data reaches the persistent backing store, the system must organize it. Standard productivity software like a word processor handles this by using the operating system's file system to save entire documents as single blocks of data. This approach fails for enterprise applications managing massive datasets. Reading an entire multi-gigabyte file just to update a single user record is too slow. Enterprise workloads require granular access, the ability to extract tiny, specific pieces of data without processing the entire surrounding file. Relational databases provide this flexibility, surgically reading and writing isolated bits of information. By enabling precise data retrieval, the database operates as a high-speed layer above the raw file system. Enterprise environments are heavily trafficked, built to handle thousands of individual users interacting with the same central system at the exact same time. This introduces the most complex challenge in data storage architecture: concurrency. Concurrency occurs when multiple distinct users view and modify the exact same data simultaneously. Usually, users operate on different sectors of the database, avoiding conflict. The critical failure point emerges when parallel processes attempt to modify the exact same specific bit of data at the same millisecond. Consider two simultaneous user requests moving toward a single integer that tracks hotel room availability. If both streams execute their modifications at the same time, the overlapping logic causes the integer to glitch into an incorrect value. In a real-world scenario, this results in two different customers successfully booking the same hotel room. Managing concurrency natively is difficult and can trap even the most advanced programmers. At an enterprise scale, the chaos of uncoordinated concurrent access is the primary threat to data integrity. Relational databases are structured to neutralize this specific threat. They do this using architectural mechanisms called transactions. A relational database forces every data access request to pass through strict transactional control gates. The transaction intercepts incoming requests before they can interact with the raw data. When multiple requests arrive, the system locks the data and queues the parallel actions, forcing them to process sequentially. Transactions also ensure that a data change is processed completely to the end, or rolled back entirely if a failure occurs. While developers must still write logic for rejected actions, the database handles the burden of state management. By enforcing these locks, transactions abstract away the complexity of concurrent environments, providing a predictable interface for architects. From a distance, the entire relational database ecosystem operates with reliability under immense pressure. The relational database maintains absolute order and data integrity regardless of how heavy or chaotic the network traffic becomes. Relational databases secured decades of market dominance because they provided a rigid, transactional backing store that guaranteed absolute data integrity. This guarantee allowed early, massive, multi-user enterprise applications to scale without corrupting their own state. Because of this reliability, the relational model became the default choice for serious architecture. However, a new paradigm has emerged. NoSQL is now a viable and often necessary alternative. This shift is driven by the limitations of the very mechanisms that ensure integrity. In a globalized system, forcing every request to wait for a transactional lock creates a massive performance bottleneck. As applications reach millions of global users, the time spent coordinating these locks across distributed servers results in unacceptable latency. The queue itself becomes the obstacle. NoSQL requires deliberately trading away some of these strict relational transaction guarantees in exchange for immense flexibility and scale. Understanding NoSQL requires looking past the new syntax. It requires understanding which specific architectural sacrifices an engineer is willing to make to push beyond the limits of relational databases.